Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book. And about 3 lessons ago, I started section 9.2 of chapter 9, which is on dynamical systems and chaos. Now I'm talking about continuous dynamical systems. An important type is the logistic map, which I talked about yesterday. And today I'm going to talk about an important mathematical constant, which is associated with a logistic map as well as a lot of other similar continuous dynamical systems. And that's called Feigenbaum's constant. So I'm going to define that and explain how you can calculate it. Anyway, let's begin. So before I do that, I want to give another plug for my series, The Math Lovers book. I wrote this from 2019 to 2022. It consists of 3 volumes, and you can buy these volumes on Amazon.com, even either in paperback or in Kindle format. I do strongly recommend it. $30 for each volume, I think, for paperback, and $9 for Kindle. I think it's a good buy. I think it's a good read. That's what I'm doing this series on. And if you don't want to spend the money, you can keep watching this series. But anyway, that's a plug for my series, the Math Lovers book. And anyway, so now I'm going to talk about the Feigenbaum's constant. And this is a little hard to read. I'm just going to cut to the chase here. And I might as well start with this bifurcation diagram, which I showed you last. This is associated with a logistic map. The dynamical system where you have x sub I plus 1 equals r times x sub I times 1 minus x sub I. So I is, but you're supposed to think of that as like a discretized time. But the variable x is continuous. It can range from 0 to 1. And this bifurcation diagram shows you the limiting behavior of x as you do if large number of iterations. And I think I showed you this last time. I'm not going to go over in detail again, but when r is between 0 and 1, the system x sub I approaches 0. That's why you see 0 on the for this graph. But then when r gets greater than 1, when r is from 1 to 3, you get again a fixed point, limiting behavior, but it no longer approaches 0. It approaches a non-zero value that increases from around 0 to 0.6. And then you get what's called bifurcation. You get period doubling. So from r equals 3 to about r equals 3.449, you get period 2 behavior. You can see that after this fourth, there's 2 values of x, 2 limiting values of x for in that range. And then you keep increasing r, you get 4, you get another period doubling, and then you increase it a little bit more, you get 8, 16, and so on. But then you reach about r equals 3.57, and then you get a transition to chaos, where it becomes basically unpredictable. So that's what I talked about last time. And, but what this guy Mitchell Feigenbaum discovered, I think in 1975, was that if you look at the size of these ranges, I might as well show you this table. Well, here's a more magnified picture. So these intervals on the bottom are the ranges of the, this is a magnified picture, but, the first range is 2, it goes from 1 to 3. Second range is about 0.449. That goes from 3 to 3.449. You keep doing it like this. These ranges, if you take the ratio of 2 consecutive ranges, that approaches a constant. That constant is called Feigenbaum's constant. It's approximately 4.669. And if you want to see some more detail, what this table is showing you here, the values r sub n. These are the values of r where you get each bifurcation. So, for instance, let's just switch back to the picture I started with. R sub 0 is 1. because that's where you start getting the period one behavior where it doesn't approach zero anymore, approaches some fixed value. R sub two or R sub one is 3 because that's where you get start getting period two to the first power, if you like. R sub two is about 3.449 because that's when you start getting period four, which is 2 squared, and so on. So that's kind of what this table showing you here. The leftmost column is just n, which goes for, just the non-negative integers. And then the middle column is 2 to the n. That's basically the period you get. And then r sub n is the minimum value of r that gives you this period. It's where you start getting this period. So you start getting period 1 behavior when r is 1, then you start getting period 2 behavior when r is 3, then you start getting period 4 to behavior when r is 3.449 approximately. Keep going like this. And what Feigenbaum discovered is if you take ratios of these differences, so for instance, the first ratio would be 3 minus 1 over 3.449 minus 3. That's about 2 over 0.449. I didn't tabulate these values, but these are approximations of Feigenbaum's constant. And if you keep doing those ratios and you take the limit, that's how, if that does approach a fixed value, that's Feigenbaum's constant. So these d sub n's approach a constant known as Feigenbaum's constant, given by the Greek letter delta, and it's approximately 4.66920. That's what he discovered. And what's even more remarkable than this, I mean, you can calculate it using the logistic equation, but you don't have to start with the logistic equation. You can start with another chaotic system, and you still get the same constant. As a matter of fact, you can start with a Mandelbrot set. I think you guys are probably familiar with a Mandelbrot set. In this picture on top, it's sort of an inverted picture of the Mandelbrot set. Usually you show the cardioid on the right. This time they're showing on the left. But you can actually take the widths of each of these lobes, each of these consecutive lobes. And if you take the ratio of the size of each lobe, the diameter of each lobe, consecutive lobes, you get that Feigenbaum constant again. But you don't have to start with that either. I mean, you can kind of think of the Mandelbrot set as a two-dimensional analog of the logistic map. You're just letting R take on constant complex values as well as real, or X take on complex values as well as real values. But you can do it with other systems too, and that's what my cover slide was showing. I mean, you can even study real-world problems. Like this one, I guess involves the amount of time you have to wait, the expected time you have to wait at an intersection for the light to change, the traffic light to change, I guess. And that is also, I haven't studied the system in detail, but you get the same behavior for the system. It's another chaotic system that involves bifurcation, and if you did the same analysis with this system, you would get the same constant, approximately 4.669. That's what we mean when we say it's a universal constant. So anyway, pretty remarkable, I think. So anyway, that I think that concludes my video for today on the Feigenbaum constant. So thank you for watching. Long live math, and I'll see you guys next time. Bye.